Welcome back to the deep dive. We're jumping into some really interesting source material you shared with us today.
Yeah, this looks fascinating. It's all about a new angle on quantum mechanics, isn't it?
Exactly. We're looking at something called spectral quantum mechanics, or SQM, and specifically how it might offer a totally new way to spot errors. They call it drift in entangled qubits.
And the really key part um, is doing this without a standard measurement, right? Without breaking that fragile quantum state.
That's the hook. So, our mission today is to unpack the main ideas, figure out why this measurement-free thing is important, look at how they actually tested it.
And maybe think about what it could mean down the road for quantum computing
Yeah.
and just sticking to the info we have in front of us.
Right. So, okay, let's get into it. This SQM, it sounds like it fundamentally changes how we picture quantum states. Less abstract, more structured.
That seems to be the core idea. Instead of just thinking about 0A and 1A as basis states, SQM maps them to vectors.
Yeah.
Vectors derived from prime factors of numbers.
Prime factors, okay.
Yeah, it suggests the superposition and entanglement happen in this kind of spectral space.
Yeah.
Think maybe less geometry and more, like musical scales, defined by the logs of prime numbers.
Huh. So, states have this hidden arithmetic ID, and entanglement is when they're harmonically aligned, like notes in a chord.
Precisely. That's the analogy they seem to be using. Coherence is arithmetic harmony in the spectral space.
Which means decoherence, or this drift they talk about, isn't just random noise.
So in the SQM view, no, it's more like a distortion, a dissonance, creeping into that specific arithmetic structure, like instruments going out of tune.
Okay, that makes sense. But then, how do you hear that dissonance? How do you detect the drift if you can't, listen in the usual way by measuring and collapsing the state?
Ah, that's the clever bit. SQM predicts these things called spectral arithmetic invariance. Basically, specific mathematical quantities tied to those prime exponents.
Oh.
That shouldn't change during ideal quantum evolution. If they do change, well, that's your signal. That's the signature of drift.
So you're looking for a change in this mathematical property, not the state itself directly.
Exactly. And they developed a specific method, the Spectral Constraint Violation via Ramsey Protocol, or SCV-RP. It's designed to sort of listen for changes in these invariants.
Okay, SCV-RP, how does that work? It's not measuring the state?
Right. It uses a sequence of quantum gates, a bit like a Ramsey experiment, if you're familiar with those. It probes the spectral structure.
Okay.
It actually introduces a tiny bit of controlled spectral drift using a phase gate. Then, and this is key, it measures something called the spectral coherence.
Spectral coherence,
Yeah.
not the entanglement fidelity itself during the drift.
No. It's set up so that if those spectral invariants have been messed up by drift, it forces a specific outcome. You get population leakage into certain states, the O to 1O and 10-air states.
So the final measurement isn't asking, is it still entangled? It's asking, did drift cause this specific kind of leakage signal to appear?
You've got it. The amount of drift is then just quantified by adding up how much population ended up in O1, OA, and 10-area.
And did the theory predict how that leakage should behave?
It did. It predicted a very specific curve, a sine-squared relationship, as the amount of induced drift increased.
So the crucial next step, did they actually try this out on real quantum hardware?
They absolutely did. The sources say experiments were run on IBM's quantum computers, specifically IBM Brisbane and IBM Sherbrooke.
Okay, the real test then. How did the results look compared to that sine-squared prediction?
Remarkably well, according to the material, especially on the Sherbrooke machine. The data apparently showed really exceptional agreement with the theory across all the drift levels they tested.
Wow.
Brisbane showed good agreement too. And this is pretty significant, right? It's not just validating the SCV-RP method.
It's the first kind of empirical thumbs up for the core ideas of SQM itself, showing that this spectral drift can be detected this way.
Exactly. Detected without that destructive projective measurement during the drift process.
They also mentioned finding something else. Spectral Sympathetic Resonance? SSR?
Yeah, that sounds like an unexpected finding during the experiments, particularly on Sherbrooke again. It seems to hint that spectrally aligned qubits might resonate together, show some kind of coherent oscillation that isn't captured by current noise models.
Interesting. Suggests there might be more structure there than we thought.
Potentially, yeah.
Yeah.
Deeper dynamics within these spectrally defined states.
So let's bring it back. What does all this mean for you, thinking about the future of quantum computing? Where does this lead?
Well, the research proposes this introduces a whole new class of tools, spectral arithmetic stabilizers.
Stabilizers. Like for error correction?
Kind of. It opens the door to what they call drift-tolerant quantum computation. The idea that you can maybe continuously monitor for these drift errors.
And maybe even correct them in real time, without stopping the whole computation or killing the entanglement you need.
That seems to be the potential holy grail here. It suggests new ways for feedback control, and really reframes how we think about quantum measurement itself.
Yeah, moving away from measurement as this purely destructive thing and more towards, like, resonance detection, a spectral analysis.
Precisely. It points towards actively maintaining and preserving entanglement, rather than just using it once and accepting that it's gone.
Okay, so wrapping this deep dive up, the core idea is pretty powerful. Use these arithmetic invariants from SQM to listen for entanglement drift.
Right. It's like listening for tuning forks going out of sync. And you detect that dissonance through a specific leakage signal, not by directly measuring the state's fidelity while it's drifting.
And this non-destructive approach keeps the entanglement safe, seems highly sensitive, and crucially, it worked on real quantum hardware.
Yes, especially that Sherbert validation, showing strong agreement with the theory, plus that hint of spectral sympathetic resonance suggesting more complex behaviors.
So this work gives us these new spectral arithmetic stabilizers, opening up possibilities for maybe drift-tolerant computing, non-destructive monitoring.
And maybe fundamentally new ways to build and control these systems.
It definitely leaves you with something to think about. If quantum information really is encoded in arithmetic structure, and coherence is its harmony, what does it truly mean if quantum measurement can become a form of resonance detection?
A very different way to look at things, for sure.